Hello, my name is Diana Thomas, and I will be presenting for you models on behavioral responses in obesity. In general, there are three different types of models. First, there are models that include behavioral responses inside their models. The energy balance models that you heard about on Tuesday are not examples of this because they're mechanistically predicting what should happen in the absence of some alternate behavior response. And that's why metabolic ward studies are very important for those particular models. There are also models that predict behavioral responses. And in these models, we would like to see what humans may do if they're presented with a certain environment. I'm going to end this talk in the last half of it with a specific example of modeling eating rate behavior so that you can really get your hands dirty and see something from beginning to end. So why do we want to model behavior or behavioral responses? Well, first, we might want to use mathematical models to assist in behavioral modification. And some of you in my group on day one said that that's why you're in the field you're in, because you would like to treat obesity by changing behavior. The second reason we would want to use behavior models or behavioral responses in our models is whether we can use those models to anticipate or understand behavior responses and thereby better inform our interventions. For example, in the energy balance models, this is what should happen. This predicts what should happen, but what we know really does happen is quite different than what should happen. What if we included what we know does happen inside the models? Well, then the next time we develop our intervention, we would be able to develop a better intervention that accounts for the fact that humans may react in a certain way. And there are also models that are used to understand behavioral responses to prevent the progression of obesity. I'm not going to present any of those today, but you can imagine, for example, something that would mitigate weight gain in some way by kind of playing to the behavioral responses. So I want to begin with a classic example of a model that includes behavioral responses, and this is one that uses social network, and it got quite a bit of media attention, and it's of interest to obesity researchers who are here, and it's also very interesting to people from the mathematical sciences. So this study was performed by Christakis and Fowler and published in the New England Journal of Medicine. And what their study was looking at was considering individuals as nodes in a social network that are connected to each other. And their responses to weight gain are interdependent with nearby neighboring responses to weight gain. So how they did this is they used data from an interconnected social network of longitudinal data from over 12,000 subjects in the Framingham Heart Study. These included family and friends and people who interacted with each other, so they were able to consider each person in the Framingham Heart Study as an individual who was connected to nearest neighbors. They examined whether weight gain in one individual was associated in weight gain with individuals in their social network. And their social network, or their interconnected nodes, would represent family and friends. Their conclusions, or their results from the study, concluded that a person's chance of becoming obese increased by 57% if he or she had a friend who became obese in a given interval. So it was a time-dependent model. And this particular article, like I said, got a lot of media attention. And I recall this was before I really was in the field of obesity. And I remember hearing things like, "Could your friends be making you fat?" as one of the headlines that appeared at the time. So it was very interesting to look at something like that. So they have some nice diagrams. If you are in the field of graph theory, you have seen diagrams like this. They're called dynamic graph theory, or it's also just called dynamic social networks. And you can see each of these nodes represents individual, and they're interconnected with other nodes, and they've been color-coded for body mass index status. And if you go to the paper, there's actually a video that goes along with this paper that you can simulate and actually see the simulations in time. So the model they applied was a discrete recursive model where generation t plus 1, BMI at generation t plus 1, was a function of the person's BMI at time t and a function of their interconnections, their nearest neighbors. And they looked out as far as 3 nearest neighbors. So they looked at a neighborhood of individuals that were interconnected to them. Those interconnections were to predict the BMI in the next step used or applied logistic regression models that predicted what the BMI status of the individual in a particular node at time t plus 1 should be as a function of all these other terms in the previous generation. So it's I think, a very simple idea if you're a mathematician. What's interesting about this, I'm going back to the first talk, the comedy of errors. A probabilist from Indiana University named Russell Lyons actually looked at this paper after the fact, after it got many hits and it was in the news. And Russell's actually, like many mathematicians, he's a teacher, he's a professor, and he teaches courses. And one of the courses he teaches is statistics. So he's a probabilist, he's not a statistician. But in the statistics class, he asks students or requires students to look critically at data or headlines and examine the statistics behind it. And the reason this particular critique came up was Russell was approached by another statistician who showed him the Christakis and Fowler paper and indicated that there was a problem. The problem was that the statistical significance tests that were applied to the estimates, which were questionable by themselves, do not show the differences that were proposed by the paper. And Russell Lyons' paper is, I think if you have, or from the mathematical sciences, you can probably get through it. He thinks it's easy, but I did not find that a layperson could probably understand fully, which is part of the problem actually, because if lay people can't understand something that's in the New England Journal of Medicine or what is incorrect in there, people would think this was up for a debate. It's not a debate. There were errors. And the history behind how Russell got the word out is very interesting. He's published that as well in the paper. One of the other issues, other than the statistical significance test, was that the models did not consider what they call the birds of a feather factor, which is not known as homophily. And what it means is that people simply associate with others that are like themselves. So maybe you pre-select friends that are the similar BMI status as yourself, which is what David calls a confounding effect. They might also have shared environmental factors that could influence outcomes. Like maybe everybody who maybe it could be a combination of both of these things. So these things weren't considered. So I'm not going to get into the Lyons social network problem, although I think it's extremely interesting, and I recommend anybody in this room to go dig up that history. It's all over the internet if you want to pick it up. But I want to go to another type of model that includes behavioral responses, and that considers obesity as an infection. And in this case, these type of models also assume some kind of interaction socially, and then that social interaction would result in becoming infected with obesity. And these kind of ideas come from the fact that if you look at the spread of obesity in the United States over time longitudinally, they look very similar to any other communicable disease like the flu. Those evolution as a video you can watch on CDC, the CDC website, look very similar. So it's not that far of a reach to use infectious disease models to model the progression of obesity. So I have here listed for you 2 different papers where they consider obesity as an infection and then model the prevalence of obesity. One is by Kazuki, who's, I'm sorry if I butchered your name, who is here right now as a participant in our group right here. And another one is our model, which was a collaboration between myself and many different researchers, obesity researchers. Steve Heimsfield, who's here, was one of the collaborators on this paper. We developed a Java applet, which is accessible on the Pennington Biomedical Research site, and you can input in parameter values, and there's a nice description of how we came up with those parameter values for our article, but you could put in other things and ask what if questions, like what if I change the birth or death rate, what will happen in that case? And you can watch the obesity prevalence curves below changing as a function. And for example, what you find is that individuals who are born into an obesogenic environment, you would think that that would be a really flexible variable that would affect and impact obesity prevalence, and you find it's not when you start playing around with this number. Another model that includes behavioral responses was a paper recently published by Emily Durander and Catherine Kaiser, John Dawson. You've heard some of these names, David Allison here, where instead of looking at the mechanistic effect, so this is what should happen, they looked at data with what actually did happen, and they compared it to dynamic models that predict what should happen. But their goal was to predict real weight change, not what really should happen, what really does happen. And so this is a very interesting publication that was published in the International Journal of Obesity, and I also recommend looking this up. It's a very nice paper. We have several models on adherence, dietary adherence, exercise adherence to prescribed lifestyle interventions. And I'm going to leave those talks to John Apolzin, who's talking about our smartphone delivered interventions, Smart Loss and Smart Moms, and adherence models that Corby Martin's going to summarize in his talk later. And I'm going to move on to the eating rate model so you can see the full development of how someone in my field or someone with the mathematical sciences may start to look at something that involves behavioral responses. The first step is really hooking your train to someone in psychology, because they are the ones that really think about behavioral responses. And my train was already hooked to Corby Martin a number of years ago. We published our first paper together in 2008. And when we were working on that article, and along with a number of other things, Corby Martin remarked to me when I was visiting Pennington Biomedical Research Center that, boy, he could have sure used me around. He could have loved having me around a few years ago, because I could have helped him with these parabolas in this paper that he was working on eating rates. And in this particular study, he was looking at something called a universal eating monitor, which is a scale. I'm going to show you a picture in a second. And people eat off the scale, and somehow they graph the data from this universal eating monitor, and it turned out to be a parabola from what I understood. I was definitely smarting from the fact that that was what Corby thought I was good for, examining parabolas, which we teach in pre-calculus. And I looked at the paper, asked him for a copy of the paper, but I didn't really carefully look at it, because I think my ego was a little blown by the fact that I was going to be brought in to look at quadratic equations. But years later, much later, a couple of years ago, in fact, I was asked by the Obesity Society. So I'd forgotten all about Corby's paper, put it aside, and I was asked by the Obesity Society to write a position statement on sugar sweetened beverage consumption in the United States. And when I was developing this position statement, David Allison showed me this paper by Demeglio Mattis, which is a classic paper on liquids versus solid intake. And this paper is actually very, very interesting. David has already shown this to you in terms of the comedy of errors, because we're looking at looking at the issue of looking at weight gain in each treatment and controls separately versus together, and then saying that there's an effect. But digging for this paper and really understanding this paper led me to one of their references. And this was the first paper on universal eating monitors. Yes, the same device that Corby Martin was using in his lab. And it turns out that that paper was really about solids and liquid consumption, whether people eat their solids faster or liquids faster and then don't feel hungry anymore. So that paper by itself is interesting. but it also was the invention of the universal eating monitor. So here's what a universal eating monitor looks like. There's a scale on a desk, and someone places their plate of food on that scale, and as they eat off that scale, they we can calculate how many grams of food have come off the scale. And in Kisselof's paper, he has published, they look almost hand-drawn, don't they, graphs of different types of curves. Cumulative eating curves is what we call it, that cumulative amount of grams that's come off the plate. So he said that this should be, anything that's curved should be modeled by a parabola, and anything that looked linear should be modeled by a line. And this took off. In the literature on eating rates, if it wasn't self-reported and it came from universal eating monitors, people investigators looked at the participants' eating curves and said either it's a line or it's a curve, and curves are more associated to poor eating habits and obesity than the lines. Well, I looked at this data and I thought about it for a minute, and I thought, wait a minute, why would it be a parabola? Really, why would, I could understand a line. You continue eating and it should be increasing function, but parabolas are, if they're concave down, they should increase and then decrease. Why would your cumulative eating curve ever decrease unless you're vomiting? So the parabola is an artificial model that was fit to this data just because it exhibited the properties of being concave down. So I asked myself whether this was the correct model and what should happen. So it seems to me what should happen, that even these people who had linear cumulative eating curves should probably, if you force them to keep eating, would they not eventually end up flattening out like this one? I mean, you could test this out, maybe have pie eating contests, but it seems to me that everybody, if you force them to eat long enough, they should eventually curve and level off if you kept forcing them to take another bite. So that is a very unique model in population biology. That's called the Verhulst model, or the logistic differential equation, with a slight modification. So I decided to see what would happen if I took the amount eaten in grams at time t seconds, the cumulative eating curve data, and model it using the logistic differential equation. Just to give you a quick picture, we show this to maybe Calculus 2 students. As E gets close to, the number of grams gets close to a saturation rate, K, this term right here becomes close to 0, and we level off. So it rises, increases, and levels off at the value of K. So that's your saturation rate, or satiety. These two parameters, R and theta, represent the initial burst of eating, or the initial time phase of eating. So initially, you would eat probably more rapidly and then slow down. In the case of the lines, they never got to the point they slowed down. They just ate and stopped. So they really only, this term here dominated. So really there's three parameters in this model, R, theta, and K, that I have to fit to data. This is data from Corby Martin's study, which we actually individually fit the R, the K, and the theta for each one of his subjects. This is what you do. You just fiddle with the R, K, and theta until the curve goes through the points, and you have enough points here to do that, to make sure that it's having a good fit. So then we started looking at some data. We looked at Corby Martin's data. I'm not going to have probably time to show you what happened with that, but it was very fascinating. But we also looked at published data, and this paper by Westerter-Plagenta was very interesting. It was a review on cumulative food intake curves, exactly what I was looking at. And in her study, she has published data from two groups of individuals. One were deemed unrestrained and one were deemed restrained. And there are psychologists here in our group that can correct me. My version of restrained eater is someone who is conscious of what they're eating and constantly trying to hold back. So it would be someone like me who looks at food labels and reads all the boxes before I eat anything because I'm deathly afraid of gaining weight. Unrestrained eaters are the opposite of that. They're not worried about it like this. So she gave the unrestrained and restrained eaters directives. One was to eat as much as you can. The other was to eat as much as they felt comfortable with. And then she recorded that data from the Universal Eating Monitor. And you can see you get different curves or different looking curves in each case. And we can calculate the R, the K, and the theta in each case. And so we did this. We calculated the R, the K, and the theta in each one of these cases. And what we find is, number one, the unrestrained eat as much as you can ate for longer time. This is not the first time I've been seeing this. I actually have looked at data from Adam Hoover's bite sensor, a bite counter who you're going to hear from, and he had the same thing, that the obese ate longer than the lean. And then I calculated the R, the K, and the theta for each one of these groups. And remarkably, there was one group that stood out. Look at the R, the K, and the theta at the very bottom row and tell me if you can see which group turned out to be different. If you said that the eat as much as you feel comfortable with, the unrestrained group, the answer is correct. The R was much higher than the other R's in the other groups, and the K was much lower. It's as if they sped right at the beginning. They were trying to eat as much as they felt they could, and then they slowed down with a very low saturation rate. So that was very interesting. And I'm not going to present the data from Corby's study, but we did run the R, the K, and the theta for every single individual in the study, and there were some trends, and they were very interesting. But I just wanted to show you, give you a flavor for how some of these models come about. It's probably my curiosity combined with hanging out with Corby Martin that brings me to that point. So just to summarize, there are models that include behavioral responses. There are also models that predict behavioral responses, and there are also models that are used to modify behavioral responses. However, there are not many, and there's very few of us working on things like this as far as I know. So for you, this field is wide open, and I know that there's a desire to include more mathematical sciences in this area, and there's a desire for collaboration in this area so that we can get further with treatment and prevention of obesity.